This next unit is on gas laws. The gas laws are very similar. We kind of take what we did in regular chemistry and then step it up a little bit and make the problems a bit harder. And a lot of the problems that deal with gas laws aren't specifically gas laws, they actually incorporate them into other things. Um, so we really this unit I kind of do like a brief introduction. We talk a little bit about the gas laws and all that good stuff. We talk about kinetic molecular theory. We also talk about the differences between ideal and real gases. Then really we spend a lot of time, a lot more time, just kind of practicing uh, AP chemistry, FRQ, and multiple choice answer problems. Because they just make the problems really hard. I don't think the concepts are necessarily that hard. It's just that the problems are kind of hard. So let's get started here. Properties of gases. So really, there's four things that we're going to be concerned about when we talk about gases. Number one is the quantity of the gas in moles, or N. The temperature of the gas, T. T is always going to be in Kelvin. So just always, always, always keep it in Kelvin. Um, yeah, just always need it in Kelvin. For any problems, it's pretty much always Kelvin. Volume. Typically, is going to be in liters, but it doesn't necessarily have to be in liters for a lot of the problems. It just really has to be in liters when we talk about ideal gas law. And then finally, pressure. Pressure is usually in atmospheres, but again, we can use different pressures for. It just really matters in the ideal gas law. Okay. A couple things to remember is that a gas uniformly fills any container. It can be compressed easily, and it mixes completely with other gases. So just keep those facts in mind as you go. Okay. Next. So let's look at some properties here. When we talk about pressure, pressure is just the measure of force that a gas exerts on a container. Okay. Now, force is a physical activity. So force is a push or pull. That's the definition of a force. And in this case, we're always talking about a push. These gas molecules are pushing on the outside of the container. Okay. Now, that is what pressure is. We can get more pressure by putting more gases in there, right? So more gas particles, we have more particles pushing, or we could have each of those gas particles have more energy or more kinetic energy. If kinetic energy goes up, each of those particles has more energy. So kinetic energy is related to temperature. So as temperature goes up, kinetic energy goes up. So that's why we get higher pressures. Okay. So again, force equals mass times acceleration. And when we talk about pressure, we're really talking about force per unit area. Okay, force per unit area. That's what pressure is. Oops, I don't want that. Properties of gases continued here. So this is a barometer. A barometer measures air pressure. Okay. Basically, the barometer, it has a vacuum up here. There's no air inside, no air. Okay. And then um, it's sitting in a pool of either mercury or water or any liquid, really. If it's mercury at atmospheric pressure, so at 1 atm or normal pressure, that's normal pressure or standard temperature. Standard pressure. At 1 atm, there'll be 760 millimeters of mercury from the surface of the mercury to the vacuum. Okay. If you were to put water in there, if this was water, the column will be much, much higher. The reason we use mercury is because it's probably the most dense liquid, the heaviest liquid there is. Okay, so this column is going to be the shortest possible. Okay, it's the shortest possible column we can get. That's why we use mercury. Okay, but really we could use any liquid to figure out the pressure. We could use water. That's also why, like, you have, like, if you have a building, so let's say you have like a tall building, right? And you want to pump water. Let's say this is water here. You want to pump water up to the top of the building. You can't just pump it straight up to the top of the building because there'll be a vacuum and the water only goes so high. Okay, so what you got to do is you got to pump the water up. And then you have to have another pool and then pump the water up. Then another pool, then pump the water up to the top. So you got to do it in stages. So there's pump stations. If you look at tall buildings, they'll on every floor there'll be a water pump to pump the water from one floor to the next. Okay. Next, it's good to have this memorized. Um, they give you, I believe, these ones on the cheat sheet, but I don't think they give you this one. I'm not sure about this one, but you really want to measure. You really want to like memorize this. It makes it really really simple. Okay, because you have to be able to convert pressures. Okay, you have to be able to convert pressures from one to another. So if you have one ATM and you want to go to millimeters of mercury, it's just 760 over 1 ATM. So you just use. I hope you guys are good at conversions at this point. Okay, so just converting, but it's good to memorize those things. Okay, next thing, this is a manometer. It's a little bit different than a barometer. Barometer measures atmospheric pressure. Manometer measures the pressure inside a sealed vessel. Okay, we often use it to look at uh, how much gas is produced from a reaction. Okay, so you'll put a reaction, make a reaction here, and then depending on how much the level changes, so the distance it changes, you can tell what the pressure is. Okay, so if you look here, oh, it doesn't want to cooperate. Hold on. There we go. So the pressure of the gas inside is equal to the atmospheric pressure minus the height of the column here, if it was less. So a manometer usually starts out. I'm just going to make a really ugly one here. Usually the liquid levels, it'll start at the same level. So liquid will be at the same level on both sides. My really ugly manometer there. And then as the reaction occurs, either the reaction takes in gas, so gas is absorbed, or it's produced. And we can tell how much pressure by taking the atmospheric pressure and adding the H, or pressure minus the H. Once we know the pressure, if we know the pressure of the gas, we can eventually find out moles of gas. Because we know that moles of gas is equal to, we can use the ideal gas law, so PV equals nRT, and just divide by RT, and we can find out what the pressure is. Sorry, solve what the moles is, because we'll know what the volume is here. We'll know what the temperature is. R is a constant, so we can figure out exactly how much gas was either created or used in that situation. Okay. Next. So here's a little practice. If we want 49 torr, and we want to go to pascals or atmospheres first. So 1 ATM is 760 torr, right? So you just do that math there. 149 divided by 760. Where's my calculator? I just brought it over here from. Oh, there it is. Okay, so 49 divided by 760. Get 0.06 TM, which makes sense. Then if we want to go to pascals, now careful. This is pascals, not kPa. The kPa given in the previous part here. This is kilopascals. That's 1,000 pascals. So they want to know in pascals. So first we got to go to kPa. So 49 torr. There's 760 torr. And 101.3 kPa. And then there's 1,000 PA in 1 kPa. So it's just trying to trick you there, but that's it. 49 times 101.3 divided by 760 times 1,000. And you get a big number, 6,531 PA. You can put it in scientific notation if you really want to be right. 6.5 times 10 to the third. And 2 sig figs. So 2 sig figs. So this should really be 0.064. Or 6.4 times 10 to the negative 2. Okay, this one, rank the following in decreasing order of magnitude. So basically, we just got to convert everything to 1 unit. So kPa, I'm going to just convert everything to ATM because 1 ATM is easy. So this one's 75 kPa. It's 1 ATM over 101.3 kPa. We have 300 torr is 1 ATM and 760. And then 350 mmHg is 760. Oops. One ATM for 760 mmHg. So you're just doing all that math right there. You get 0.74 ATM. You get 0.39. And 0.46. And then you should be able to put those in order. I'm not even going to do it. I'm not going to waste your time. You can figure that out. That's cool. Like, selected that specific thing. Anyway, moving on. Stop doing that. I just want to move the thing. All right. Now we're going to look at the gas laws. These are the only ones we're going to look at the moment. Boyle's, Charles, Gay-Lussac's, Avogadro's, Ideal, Dalton's, and Graham's. Actually, I guess those are the only ones we're really going to look at. We're also going to look at root mean squared velocity later on and van der Waals equation later on, but those aren't really that important. These are the important ones. Important. You need to know all of these. These 3 right here are all combined into this one, but it's good to know which one is which, B, C, and G. And then you have to memorize all of them. So you should memorize. Let's go through each one. So Boyle's law is the relationship between pressure and volume. It's the only one that's inversely related, so inversely proportional. However you want to memorize that, feel free. But it's P1 V1 equals P2 V2. Basically, initial pressure, initial volume equals the resulting pressure and resulting volume, and temperature and number of moles, or N, are held constant. That's important that we're holding those two things constant. Okay, so as pressure goes up, volume goes down. They're inversely related. Okay, doesn't matter if what pressure and volume units don't really matter. They just have to be consistent. To save yourself time, if they don't ask you to put it in specific units, then don't put it in, put whatever units that they give you. Okay. Next one. So boils, again, we're looking at the relationship between pressure and volume. It's really, really simple. As we increase the pressure, the volume is going to decrease. We just squish it. It's squished. Okay. If we graph it, you'll see as pressure increases, volume decreases. Now, it's not perfectly linear. It's not perfectly linear, but that's okay. That's Boyle. Next, Charles. Charles is the relationship between volume and temperature. Okay, as volume goes down, temperature goes down. Okay, or really, as temperature goes down, volume goes down. Okay, here it's important though, temperature must always be in kelvins. Always, always be in Kelvin. Okay, the reason that, okay, and then also pressure and number of moles are constant. So you'll notice that all of these laws, there's always two that are constant. This one's pressure and number of moles. Okay, so as you decrease temperature, you're going to decrease kinetic energy, which decreases the volume. Okay, the volume is going to get smaller and smaller. That is if pressure is allowed to stay constant. When we look at a balloon, we assume that the pressure is constant because it's allowed to expand and contract. It's not really 100% true, but it's close enough. Okay, let's look at Charles' law practice. So these are pretty simple. A sample of gas, 15 degrees Celsius. We need to convert that to Kelvin, 273 K. Sometimes I like to write out, I actually like to write out, so temperature 1 is 15 degrees Celsius, and volume 1 is 2.58 liters. What volume? We want to know what the new volume will be if the new temperature is 38 degrees Celsius. So again, we have to convert to Kelvin. We have to. We must convert to Kelvin. So add 273, add 273. Okay. It's like always the first step you should do. Write out all your variables, okay? Convert everything to Kelvin. So we get 288 and 311. Okay, and then we know V1 over T1 equals V2 over T2. And we just plug in the numbers. So 2.58 over 288 equals V2, which we're trying to find, over 311. Okay. We can multiply both sides by 311. And we'll get our answer. So I'll do my calculator. So 2.78. Just ask yourself, does that make sense? If we increase the temperature, what's going to happen to the volume? The volume should go up. So yes, it makes sense. I always ask myself if it makes sense. Okay, next, Gay-Lussac's law relates pressure and temperature. We hold volume and number of moles constant. And these are, again, directly related. Pressure goes up as temperature goes up. That's simple. Okay, temperature must be in Kelvin. Doesn't matter what pressure is in. Now, all of these laws combine together to form the combined gas law. And really, this is the only one you really need to memorize. PV over T equals PV over T. If you hold temperature constant, so number of moles is always constant here. That's the only one that's held constant. All the other ones are changing. But if you hold temperature constant, so you just say, okay, let's say there's no temperature, or temperature doesn't change, now we have boil. Right? That's Boyle's law. No. There we go. Okay. Now it's cooperating. Okay. If you hold volume constant, now you have Gay-Lussac. So P over T equals P over T. If you hold pressure constant, now you have Charles. V over T equals V over T. So if you memorize this one, you can just figure out the other ones. Okay, so Avogadro, call it a combined gas law. Sometimes they call it Avogadro's law. I don't like to call it Avogadro's law. I just call it the combined gas law. Okay, so let's see. Suppose we have a 12.2 liter sample. So volume 1 is 12.2 liters. It contains this many moles of oxygen gas at a pressure of 1 atm and a temperature of 25 degrees Celsius. If all this O2, so the O2 is staying the same, the number of moles is staying the same. Number of moles is constant. Doesn't matter that the type of gas is changing. It doesn't matter. Okay. At the same temperature and pressure, so temperature 2 equals the same, pressure 2 equals the same. What would the volume be? So it's saying here that if we have the same number of moles, the same temperature, the same pressure, then the volume will be the same. So V2 will be 12.2 liters still. Kind of a trick question. Because all this stuff is saying the same. Temperature is 25, pressure is 1 atm. So if all of these stay the same, the number of moles is staying the same, then the volume should stay the same. Tricky question there. Just trying to trick you, I guess. The only thing I could think of is that they're asking. Oh, I guess maybe if they're. Maybe are they talking? Are they saying that this 0.5 moles is now going from O2, O3? So really you have 2/3 the number of moles. I guess that's what they're saying. If that's the case, then you'll get 2/3 the volume. So it'll be 12.2 times 2/3. think that may be what they're saying. So 8.133 liters. Yeah, that was a tricky. This is a tricky question. Again, this is I think taken from the book. This is a book problem. It's been a while since I did this lecture, obviously. So yeah, I guess they're saying that we're getting, we're taking this, we're getting 2/3 of this 0.5. So that's the pressure should be 2/3 of what it was. So 8.133. And I think this is right because I remember looking at the answers to this, and that was, I think, the answer. Yeah. Okay, the last law here. The last law is the ideal gas law. Oh, not that last law. We have a couple more. Ideal gas law combines all three and incorporates the number of moles. Okay. In this case, pressure must be in ATM. Volume must be in liters. R is 0.0821. Okay, and the units for that are liter ATM over mole Kelvin. Okay, it's just a weird unit, but that is what it is. And then temperature has to be in Kelvin. So this is the ideal gas law. We're just using it for all four quantities. Let's just look at one practice here. So sample of hydrogen gas is a volume. So volume equals 8.56 liters. A temperature is 0 degrees Celsius. So T equals 0 degrees Celsius, which is 273 K. And a pressure of 1.5 atm. Calculate the moles of H2 molecules present. So pressure is 1.5 atm. You don't have to write the units when you're writing out the work here. Volume is 8.56 liters. N is what we're trying to find. R is 0.0821. And T is 273. So we got to solve for N. So divide everything by the 0.0821 and 273. And N should equal 0.372 moles. Okay. Okay, next, partial pressures. Oops. So this one's really simple. The total pressure is equal to the partial pressures of all the gas in the mixture. Okay, you can use the mole fraction. You can use mole fraction to figure out what the partial pressure is if you know the number of moles of each one. Okay, mole, and the mole fraction is just number of moles of part. It's part over whole, right? So the moles of whatever you're looking for over the moles of everything. And then if you want to know the pressure of that specific molecule in this in the thing, it's just you take the pressure, or you want to know, if you want to know the pressure of that individual gas, you take its mole fraction times the total pressure, and you'll get it. Okay. Next, moving on. I'm trying to go a little faster here. Graham's law of effusion diffusion. This one's a little bit confusing. So diffusion is when you put a gas inside a room. What does it do? It tends to spread out. That's diffusion. It spreads out, spreading out. Effusion is if you have a container and it has a small little hole in it, the gas will escape, will leave the hole. So effusion is escaping a hole. And the rates are always, you can measure the rates the same way. The rate of gas A over the rate of gas B is equal to the square root of the molar mass of gas B over the molar mass of gas A. So just be careful because these are flipped, right, compared to this. So just got to be careful there. So let's look at one of these problems. Calculate ratio of fusion rates for hydrogen and uranium hexafluoride. Oops. I don't feel like doing that one. Let's do this one. A pure sample, because this one's tricky. A pure sample of methane is found to have fused through a porous barrier in 1.5 minutes. Under the same conditions, an equal number of molecules of gas fuses through the barrier in 4.73 minutes. So the same number of moles. So N over 1.5 minutes over N in 4.73 minutes. Okay, this is the tricky part here. You need to put N, the number of moles over that, number of moles of that, equals the square root of the molecular mass. So this is, let's call this A and this B, right? So this is the mass of B and this is the mass of A. So A is the one methane. Methane is CH4, so that's 16 grams per mole. And we don't know we don't know this. That's what we're trying to find. Okay, the tricky part again is that fact that we need these n's here, because it's not that the rate isn't 1.5 minutes, it's n in 1.5 minutes. And this is n in 4.73 minutes. Okay? So when we do this, remember if we take a fraction divided by a fraction, so it's like n over 1.5 divided by n over 4.73, we flip the second one, so it's n over 1.5 times 4.73 over 1.5. Okay? So this becomes 4.73 over 1.5, flips. And we square both sides, squared. So I'm going to erase some of this, make it a little bit neater here. Okay. So we square both sides, so x over 16. So that squared times 16, multiply both sides times 16, that will give you your answer. So 4.73 divided by 1.5 squared, quantity squared, times 16, you get 159.1. X equals 159.1 grams. All right. All right, we're going to stop there. If you have any questions, which I'm sure you might, go ahead and ask. Work on that worksheet that I gave you. And yeah, it's a lot of kind of review from last year for all this stuff. So good luck.